Hello everyone, my name is Sahil Khose, and it's been a while that we have done such a live stream on my channel. So this channel is primarily about having research paper explanations, and it's just my way of getting into the depths of research papers and in machine learning and artificial intelligence, and getting it to you guys through this medium. And it's so the reason it's been a while that I have had a major life update. I've completed my bachelor's, so I'm yet to get my degree, but I've completed my bachelor's recently, and I've moved to Atlanta right now to pursue my master's in computer science at Georgia Tech. So it's been like a hectic time for me to shift here, and I've settled in. I've had my first week of lectures, and hopefully I'll be getting these research paper streams more often uh, right now. So this is a completely new setup for me. So new laptop and all of this. So I'm just gonna go ahead and check if everything is running all right. I think we can see a comment that everything is all right. Cool. So the paper today we'll be talking about is vision transformers, as mentioned in the title, and the title of the paper is "An image is worth 16 by 16 words: transformers for image recognition at scale." So ever since attention is all you need by Vasani et al. Came was introduced in natural language. Transformers have dominated the space in natural language processing. All the architectures have been replaced by transformer-like architectures in natural language, and ever since, and have gotten like very amazing results. But the same was not true in vision uh, because of very obvious reasons that we'll get into. Main reason was the compute and the resources required to process vision data sets is extremely high. So transformers didn't really come into picture in vision until 2 years ago. So it's September 2022 right now. So around 2020, transformer like architectures were being talked about in vision, but this was the first paper that we'll be looking at today that actually got amazing results and convincing results using a transformer like architecture in vision applications. All right, so I still can't see your video here, but as we have the comments on, I think everything is all right. So we'll just go ahead into the paper and we'll have a look at more details of what it does. So as I mentioned, so this paper was released in 2021 on archive 3 June, and 16 by 16 words is just going back to what tokens are in uh, natural language. So words would be tokenized, and you will be passing these tokens into your transformer. So image is worth 16 by 16 words. So words is the unit that goes into the natural language transformer, and they are trying to replicate that, saying okay, an image would be a 16 cross 16 grid, and that would like first those patches that are created would be considered as words analogous to what it is in language. So as I have mentioned here in the abstract, that attention is applied. So attention has been in natural language for a while, and it has been applied in conjugation with convolutional networks, and also used to replace certain components of convolutional networks while keeping the overall structure of the architecture in place. But the reliance on the convolutional networks has not been there up until this paper. And what the authors show that when pre-trained large amounts of data, so this is the key takeaway from this paper, is that transformers require pre-training on large amounts of data in any form. So in language it would be a self-supervised manner. Self-supervision is yet to break, so it's broken down in vision, but it hasn't seen as impressive results, or there are no simple recipes for self-supervision in vision, self-supervised learning in vision for conducting these huge transformer pre-trainings. So pre-training could either be self-supervised or supervised in the case of vision, but it's predominantly self-supervised in the case of language. So the main takeaway is when pre-trained on large amounts of data, uh, these vision transformers can be transferred to multiple uh, vision benchmarks, and are able to outperform or match the state of the art that you have right now, while requiring um, So they also mentioned that these models that they have generated, vision transformers, are require substantially fewer computational resources to train. uh, we'll directly go ahead and look at the crux of so how exactly the architecture is working, and then yeah, I'm still for some reason not able to see my own video. All right, yeah, I can see that. Good. So this is the main architecture that we are going to look into. They take this image, and this image is passed. So in this particular image, it's shown it's like a nine grids are there, or nine patches are there. It's divided into 3 by 3, and every single patch is going to be passed into like as a token, as we have in natural language models. So these are 9, and so basically this entire thing is your model. I don't know if you can see my, yeah, let me just, yeah, now you'll be able to see. Yeah, this entire thing is going to be the vision transformer, and this is your input image. It's split into patches. Then these patches are essentially passed into this transformer encoder after being embedded with the positions. So because transformers, when they take in these tokens, they are unaware of what token was, like the position of the token in natural language. So was it the first word, second word, third or fourth word, or in an image it would be a two-dimensional position. But so some kind of notion of a position embedding has to be embedded into these patches, so that the transformer learns the spatial location and is able to get better information. And then you also add a CLS token here, and basically you just pass it through a transformer encoder. It goes through an MLP head in the end, not the entire thing. So all of these encoders, encoded patches are not used in the final version. You could use it, but it's the performance does not degrade a lot. But you input or add a new CLS token, which essentially summarizes. So it does not have any patch or any image patch that is an input to it, right? So all these, so this will run all in parallel, right? So the first patch that is inputted to the encoder will the transformer model will learn deeper and deeper understanding of that patch that was given as an input, and the output of that particular patch in the end of the transformer encoder will have semantic information about the corresponding patch. So you will have semantic information of all the patches. Hence you add a CLS token, which, because it's self-attention, and you will have a quadratic mapping. So you'll have one to all mapping. So every single token will attend on every single token that is around it. You will have an aggregation. So the CLS token will have access to all the other tokens in the image, and hence it will be like an aggregated information. Because it does not have an input, it will be an aggregated information that we take from other patches. And the only work this output token will have would be to aggregate the information of the entire image, and then that we'll use as for downstream tasks like classification. All right. So as we learned earlier, why vision transformers took a bit more time than language transformers is because of a very simple reason. Okay, I need to switch my position. Yeah, you'll be able to see. So attention is quadratic computation. So if you have 500 tokens in NLP, which is usually the case, you will have 500 square connections, and this will be computed every single time you compute your attention module. But in images, that's not the case. So like sentences or paragraphs which are inputted in natural language would be 500 tokens long maximum. Won't be in, like, it's rarely that it goes in 4 digits. But images, like even a data set as old as ImageNet will have 250 pixels by 250 pixels, and that's very small image in dimensions when you consider modern photography and the modern image that we are viewing. So we deal with millions of or tens of millions of pixels every single day when we are looking at images, videos, and high stream quality content out there. But even if you consider a very old data set like ImageNet, it has 250 pixels by 250 pixels resolution into three channels, but that's all right. That will have those many numbers, 625,000, so like 500,000 of tokens. That will give you 10 power 10 connections, and you're still at like, this is, yeah, no amount of compute or like all the Google resources, or like not just Google, like take every company and add up the resources, they won't be able to make these computations for large scale data in vision. Hence what ViT is like, okay, let's just do patches. And so as the title mentions, there are 16 by 16 words, so images represented by 16 by 16 words, and that is going to be 256, and that is much richer. So that would be again in the realm of what we dealt in natural language, right? And yeah, that was the main bottleneck that we had when we were trying to bring this transformer architecture in vision. And why is transformer architecture, or like what is transformer architecture? uh, so it's not necessarily a single component of transformer architecture or the design of the transformer architecture that makes it very special to solve these problems in natural language and vision, but it is basically, so when you think of vision, you will think of CNNs, right? When you think of natural language, you think of LSTMs. Now, the range of non-linear functions that these two architectures can map is lesser than the range of non-linear functions that a multi-layer perceptron can attend. Just because every single node in a MLP attends to every single, or like connected, not attends, it's connected to every other node from the previous layer and the next layer. So you have a lot of freedom there, but it's not the case with CNNs and LSTMs, where in LSTMs you won't be able to retrieve information from like further away tokens, or like in words. And in CNNs also, it's the computation is local in nature because of the filters that's moving across. So you won't really have information access until deeper into the network, when your field of view field of view is the entire image, essentially, when the filters, like, it gets reduced to the filter size. But until then, you won't really have access to all the other. So we can just consider the, like, in vision, one patch would be one node. It does not have access to all the other nodes in the previous layer itself or the next layer. It's very local in nature. So these are constraints that we have put into on these architectures to solve problems in language and vision. So CNNs and LSTMs are so are less general, or like MLPs are more general than what CNNs and LSTMs are. And transformers, because it has the exact same nature of MLP, where one node is connected to all the nodes previously and all the nodes in the next layer. Not just that, it also attends over it in a fashion that MLP does. But what the exact difference is, MLP has fixed weights irrespective of the inputs. It has fixed weights that the existing node will attend to the previous layer nodes, right? So those weights are fixed in nature. Once your training is complete, those weights are fixed. But transformer is more general in a sense that even these weights are dependent upon what the input is. So it depends upon actual content of the node itself. Hence, we would say that it's a dynamic weight MLP. Hence, we will say that it's a dynamic weight NLP. And these constraints that we were talking about earlier, when we have in CNNs and LSTMs, these are inductive biases. We'll look into this phrase and what it means deeper as we go in ahead. But these are called inductive biases that are introduced by humans, and why that has been the case, and why we're moving away from it. We'll get into like next into the paper, right? So essentially, this is the architecture that you have. You slice it up, you pass it through linear projections of flattened patches. So uh, you flatten this out, you lose the spatial dimensions here. You flatten this out, you pass through a linear layer and project it to a higher dimensional vector, and then you add positional embedding to it. Positional embeddings are added in the sense, so there are different kinds of positional embeddings they have tried around with. So the earliest of works had used sinusoidal waves in NASA language, but these use learnable position embeddings. So it just fetch the learned vector or the embedding for the first patch and so on, and that seemed to be working very well for them. They also tried 1D versus 2D position embeddings, and there wasn't much of a difference. The highest jump was between not using any position embeddings and using 1D position embeddings, and 1D performed very good as compared to the others. Hence, we just kept that. And the transformer encoder. So if you have background with natural language and the transformer encoder was there, I've attached Vaswani et al.'s figure into the right of this figure so that we can compare exactly what the differences have been, right? So yeah, so this is the transformer encoder that is used in vision transformers. This one, you have the embedded patches, you pass it through a norm, then multi-headed attention, then you have the residual connection, again followed by a norm and then MLP, and this encoder and a residual connection, and this is reiterated multiple times, right? Now the main difference is, if you see the encoder of this of Vaswani et al., we do have multi-headed attention first and then a feed-forward network next, but the add and norm, so the add still stays the same, but the norm was after multi-headed attention and feed-forward network in Vaswani et al., but in this paper we'll have it before the multi-headed attention or the feed-forward network. And this was the case because this has been the case because a lot of experiments in natural language and vision transformers came into place, and people figured out when you're using training such large models and over such large data sets, what happens is the training is more stable and it performs better. So these are like little small tips and tricks that come up when you're empirically training large models or large data sets. So they figured out that if you have the normalization before these blocks, it performs better and the training is probably more stable. And yeah, it just the observation was just that both of the encoders are very similar to what they were, and that was actually the main point that they wanted to make is, okay, let's just use the same transformer encoder and we'll see what happens, right? Yeah, the figures are really informative here, so we'll just go ahead and look at those. So these are the multiple model variants of different sizes. ViT base, large, huge, with the next one larger or having more parameters than the first one. So the first one has 86 million parameters. Then we have 3.5x jump to 307 million parameters, and again a 2 times jump, or like the first and third will have like 7 times jump number of parameters. So ViT B, ViT L, ViT H, right? So these are the model variants that they have tried, and then we'll go ahead and look at the results that they have displayed, right? Yeah. So the results are okay. As you can see at the top, it's a conference paper at ICLA 21. Yeah. So they have trained on a bunch of datasets, very famous vision datasets: ImageNet, ImageNet Real, CFAR 10, CFAR 100, and so on. And what they essentially show is, so the left part of this diagram of the table, has the vision transformer results, and the right side of the table, so I have divided it. You won't find it in the paper that is divided. The right side will have the previous SOTA of ResNet as well as EfficientNet, right? As you can clearly see, the bottommost row, you can see that it took like 12.3k TPU V3 core days for EfficientNet to train, and 9.9k TPU V3 core days for ResNet to train. And every single model on the left is tremendously cheaper when you look at TPU-v3 core days, but it's still the ironic part about it. So is that the competition is still in thousands of TPU-v3 core days. Hence, it's still not viable for like small researchers to extend these problems. But yeah, it's just a bit ironic that they have mentioned that it requires magnificently more less number of training resources. That is true, the case is true, but it still requires thousands of TPUDs, right? Alright, so as you can see, the largest model has all the best metrics apart from just Oxford class, and it's 0.06 difference. But still, like every single model here is crushing the previous SOTA by convolution neural networks in the resonance and efficient nets. Alright, so another small detail about the results is slash, so ViT would be ViT, the vision transformer huge. The slash 14 represents the size of the patches, so it's like a 14 by 14 patches. So if you have smaller patches, so like the resolution of the patch is smaller and smaller, computation will be higher because you will get more number of tokens, or like higher resolution images will also lead to more number of tokens, but more number of tokens will lead to more computation, but you'll get better results at it because your field is smaller, the patch that you're tokenizing is smaller, so you will get more information. But the others are just 16 by 16 patches, which have been used primarily in this paper to report all the results. Observations made below. The first row here determines what dataset it was pre-trained on. So JFT is a dataset. JFT 300 million dataset is a in-house Google dataset. It's not made, it's not released to the public. So the pre-training was done on 300 million labeled images on this dataset, and so the first two models are pre-trained. These two models are pre-trained on this JFT 300 million dataset, and then fine-tuned to the other datasets that you can see on the left. The third model here you can see is pre-trained on ImageNet 21K. And the other models were not, like this is not mentioned. The pre-trained dataset is not mentioned, so they are just trained on the dataset that are given, right? Moving on, so there are a couple of observations here. ViT pre-trained on JFT has better results than ResNet, additionally with less resources. Second observation is that ViT pre-trained on Image 21K is also good. So it does not necessarily require a large dataset like the JFT 300 million. Even on if you pre-train on Image 21K, you can see it has competitive performance with the previous state of the arts and CNNs, right? Moving on to the next diagram. Yeah, so this is they have also performed. So the last data set that you can see here, it's VTAB in the previous table, is that they also train on the benchmark, which is a low data benchmark. You have only 1000 images per task. It's called visual task adaptation benchmark, and there are 4 task groups in it, and you can see that vision transformer is able to bit. So ViT was also paper previously released by the same set of authors, and that's marked like second column in these diagrams, and you can see that vision transformers are every single time is able to outperform even in like low data benchmarks that we have around here. It just shows that the fine-tuning is not just does not just work on like huge vision datasets, but even small vision datasets they do perform well, right? So this is another fascinating example that they have given here. It just goes to show that there is one very important takeaway in this. Let me just move my photo. Yeah, so there is a huge takeaway from this diagram which says that the number of pre-trained examples that you're using are very important and vital for these vision transformers to perform and outperform these convolutional neural networks, right? So the larger the pre-training data set, the better the performance of these vision transformers would be. And for these vision transformers, To outperform the convolutional neural networks, neural network architectures, the key point is to have very huge pre-training dataset, right? So as you can see, ImageNet and ImageNet, like, so these gray lines over here, they represent convolutional neural networks, BIT benchmarks, and the other circles that you can see are vision transformers, right? So CNNs outperform vision transformers when you have pre-trained. So 1.3 million images are there for ImageNet, and so on, like 14 million and 303 million. So as you increase the pre-trained number of pre-training images of the data set, these vision transformers, especially the larger ones, start going up, and they uh, you can, as you can see in the last column, that they do outperform the supervised benchmark that we have. But interestingly, uh, the smaller sorry the smaller model of vision transformer outright here when pre-trained on ImageNet is able to outperform the larger models here. So this is very fascinating. So the key takeaway is that for transformers to outperform, we have seen this in LS teams as well, or in natural language as well, that you need huge amounts of pre-training for these transformers to actually outperform these networks, right? And because self-supervised pre-training is not big in vision yet, we are yet to solve how we can pre-train in vision using self-supervised learning in a very efficient manner, and use that tactic. So we are again trying to bring in the concepts from natural language to vision, and we are able to see, so some kind of pre-training we are able to achieve right now, and we can see that these transformer models do require a massive label data set for the pre-training purpose, and only then they are able to beat the conventional neural networks in performance, right? Yeah, so this was the ImageNet top 1 accuracy that you saw, and even in JFT we see a similar pattern, is that a number of JFT pre-training samples, so they train on 10 million samples and 30 million, 100 million, and the entire data set, and we can see that BITs, sorry, the CNN models, the ResNet models in the gray and black, are like plateau very soon, but the vision transformers do not plateau, or especially the larger ones. So you can see at the top, these do not plateau very soon. So it shows that we still have a long way to go to scale these transformers, vision transformer models, to get even better results. And you can see that vision transformer is able to beat only when the number of data samples are larger than, for the pre-training task, is more than 100 million, or else you are just better off with the CNN, right? And this one on the image on the right was linear 5-shot image at top 1% accuracy. They also have like a hybrid model that they have checked, and they can see that hybrid model does help when the pre-training is in the, like, there is not a lot of pre-training, but when the pre-training is huge, again vision transformers are just outperforming both the hybrid model. So hybrid model would be CNN. So first 4 layers of ResNet, you abstract the feature, and then you pass through a transformer model, vision transformer model. So but when you have huge pre-training, vision transformers are again dominating both convolution and hybrid networks, right? Yeah, you can see there's an inspection over here, that we are just mapping back what the vision transformer was attending on when it during test time, and you can see that it is attending on correct areas. So just the dog is highlighted, the airpin is highlighted, yeah. And yeah, these are like couple of very insightful images right here. Is that this first one shows that these are basically like the filters that these transformers learn, RGB embedding filters, and they apply principal component analysis to attend that. And you can see that these are very similar to what we saw previously in Alex, that we have such similar filters in the earlier layers to abstract out information. Position embedding similarity, again 1D embeddings are visualized in 2D, and you can see that these embeddings that are learned are actually learning the exact position that the patch belongs to in the image. And this is the most like one of my favorite images out here in this paper is that uh, on the x-axis is the network depth of different of vision transformers. On the y-axis you have mean attention distance of pixels. So basically every single token, how far away does it attend to or look into, uh, and you just average it over through all the tokens that you have. So in vision transformers you can see in the earlier shallow stages as well, every single token attends on like smaller and larger, uh, like near also and far away also. But when you get deeper and deeper, it just attends globally. So you'll just have global attention because you need global context in the end, not local context. So you'll see a lot of local context in shallower layers, but only global context in the deeper layers. But this is very specific to vision transformers. As you can see in the blue, CNN would have something like this, because global perception increases with depth because of the convolutional layers, the field of view increases. So this will just be a line in CNNs, and this the green part over here, the shallow networks, is why these vision transformers are getting better results. Like one of the reasons that it is because every single patch is able to attend globally as well, even in the initial layers, which CNNs can't, right? So that's pretty fascinating that we are able to see that. And yeah, we go ahead. So there are a lot of videos on vision transformers out there. Yeah, Epiphany and Yannic Kills, obviously. Great Yannic Culture had have videos, so I would recommend you to go check them out. And they are just some notes that on Yannick's videos that he commented. So it's like history is like first attention was introduced in LSTMs. Transformers then completely replaced LSTMs in NLP. Transformers were paired with convolutions and vision, and now transformers are replacing convolutions and vision completely. As you can see, it is dominating all the results that we are looking at. It's a bit ironic to talk about substantially fewer resources and regimes of thousands of TPODs. And here's the point of view that Yannick had and why transformers are ruining everything is like LSTMs and CNNs, we had a good inductive prior. So those restrictions that we talked about earlier are called inductive priors or biases that humans have to introduce. So MLP can technically learn any function, right? So it's more general than LSTMs or CNNs. Now, right. CNN's inductive prior is that pixels care about their surroundings. This is the inductive prior that humans uh, put into the like enforce into the architecture. Or LSTM inductive prior is that take one word then another. So the temporal conditions are preserved, right? So prior will be used co-equivalently as bias in this discussion that we add. So this prior is the bias that humans add so as to learn effectively, because we don't have infinite data or we don't have enough data. If we have infinite data, then we can go with the most general architecture that we have. Then it will be able to learn any the exact mapping function, the global optima that it has to learn to get the best accuracy out there. But because we don't have enough data, these inductive biases have to be introduced by humans, uh, for these architectures to perform well. Now regime is that we have a ton of data. As we saw, JFT has 300 million labeled images. Our prior bias is not good enough because data is tending to what, like big data, right? And transformers are more general in MLPs because it has this dynamic weight that it has associated uh, because of the attention network that it has, and that MLPs are way more general than what CNNs and LSTMs are. Hence, with ton of data, the performance goes up, and these transformer architectures learn useful biases. So like you can see scheme filters of CNNs were used right in figure 7, but they are able to learn better biases. So these filters that they have learned, they might not, so they on superficially they look similar, but they might be just enough different and better than the inductive biases that we have created, that they are able to extract those feature like those representations, and are able to get a better accuracy than what we could with conventional neural networks. So they are learning better biases, and as you go down the lane, it's like more inductive biases. So the future that Yannick thought could be future work for this paper would be skip connections as very strong inductive biases, and they are still there in every single architecture, including transformers and vision transformers, because you are pushing in. So you want the you are pushing in a signal as it is completely through the skip connection. And that is a very strong inductive bias that we have. That should be mitigated next if we want to get even more general networks, but that has a as I mentioned, it's be far off in the future, and they should go with magnitude of more data, right? So magnitude of more data will take a lot of time, and when that is true, probably this inductive bias will also go away, right? They also talk about that resolution adjustment and patch extraction are the only points at which inductive biases about 2D restructure of images is manually injected in this vision transformers. So inductive biases like resolution adjustment, so different pre-training and fine-tuning resolutions will change some things, and patch extraction, so this art of slicing up this particular patch and then going ahead is also on introducing an inductive bias. So apart from residual connection, these are the two biases that seem to be still there in vision transformers. And going ahead, if we remove this inductive bias and we have a larger scaled data set, then we'll be able to probably achieve even better results going down, right? So this was one of the papers that we have been so this is one of the papers that we have been that we read. This was the first paper that we read at the course that I am attending in my fall 22. It's by Dr. Jody Hoffman, machine learning with limited supervision, and this was the reading that we did. And one of the things that I wanted to do with this architecture was not just read the paper as I always do, but also get into have like a quick implementation just to understand the paper in deep. So we also have a GitHub repository, as you can see here, that we made, like Noob Speedrun. It's a collaborative effort with Aditya Kane, and we allocated like 2 hours to understand, discuss, and implement whatever we could. We don't have the training ready yet, but we will be doing that. Right now, what we have is we have the models ready. It's a very noob implementation. We just wanted to get essence of what it is doing. So before getting into the model, there is a patchify script here, which basically does the patchification of the image that you get. And after that, then you have the model where your position embeddings are so this is in no way is trying to replicate exactly what the paper is doing, because they are doing more complex stuff, but we want to get the essence and implement something as quick as possible, while keeping most of the things similar, at least at a higher level. So position embeddings are not learned embeddings here, so our to do is learned embeddings should be there, but we wanted to just make a quick implementation just to get so we just have scalar values that we add here, or the encoder is the encoder that we use. So there is another to do here, try not to share weights in the layer norm, and like it's a very basic implementation to get a gist of how the model is working, or how the architecture is. Hopefully we'll be doing this for later architectures or people that we read, but vision transformer was a very clear decision for us because it has been on our mind for a while. So you can go ahead and check it out at Aditya Kane 2001 / no speedrun. The links for my annotated paper, this repository, the 2 videos by Yannic and the AI Epiphany, everything will be listed below. And right, I just read the paper, and with that we've hit the golden mark of 40 minutes, right? Almost all of my videos have been around this time, even though for some reason, like every time I'm like, okay, this time we'll make it shorter, 20 minutes, 30 minutes, but I somehow end up going to the 40-45 minute realm. That's all for today, guys. Thank you so much for being here and supporting me. For everyone who's been here, this is my first video. I think this is the 19th paper explanation that we have had here. So not necessarily the 19th. We have had videos where we have discussed 3 or 5 papers as well. This has been the 19th time we are doing that. Apart from the streams, I also streamed a couple of times about coding some normal, like something that I was thinking about and just trying out, identifying some research interest and reading those blogs and trying to implement something. So even those are there out there. Thank you everyone for being here, and hopefully I'll see you next week. See ya.